Okay, ma. So next concept we are studying is capacitance, ma. But before that we will study about what happens when conductor is placed in a electric field, ma. So this is an electric field, uniform electric field. Okay. So this is an uniform electric field, ma, and this body is a conductor, or you can call it as a metal, any metal. Any metal is a conductor only, no? Clear, no? So if I place a metal in an electric field, can you say what happens, ma? If I place a metal in an electric field, what happens? See, ma, this metal is consisting of free charges, no? Metal always have free electrons. And these free electrons, they will experience a force in which direction? In the direction of electric field, or in opposite direction to the direction of electric field? Negative charges, negative charges. Negative charges, they experience force in opposite direction to the direction of electric field, no? Clear, no? So therefore, all these negative charges, they travel to one end of the conductor. Okay, ma? All the negative charges, they will deposit at one side. If negative charges are depositing on one side, it means the positive charges, they are depositing on the opposite side, no, ma? Are you able to understand? So therefore, what is this field? This is the external field which we have applied. Okay? But internally, there is one more field which is developed, no? Internally, here there are positive charges, and here there are negative charges. So here also a field develops, and what is this field called? This field is called as induced field. Okay, ma? What is this field called? This field is called as induced field. Okay. Now what is the direction of this induced field, ma? So this induced field is exactly in opposite direction to the direction of applied field or external field. Okay. So therefore, inside this metal conductor, the external field and the induced field, they get cancelled with each other. Are you able to understand, ma? So if they get cancelled with each other, then what is the net field inside the conductor? Net field inside the conductor will be 0. Okay. So therefore, make some important points, ma. So inside the conductor, okay, negative charges get deposited. Negative charges get deposited in opposite direction to direction of electric field. Okay. So positive charges get deposited. Positive charges get deposited on the opposite end. Okay, ma? So an induced field, E induced, develops opposite to the direction of E external, such that E external plus E induced, they will become equal to 0. Clear, no, ma? So therefore, applied electric field and induced electric field, they will get cancelled with each other. Therefore, what is the net field inside the conductor? Net field inside the conductor will become 0. So this is one point which you should understand. Okay, ma? So therefore, if this is the metal conductor, clear, no, ma? So electric lines will be just passing out of the conductor. But inside the conductor, net electric field will be how much? Net electric field will be 0. Okay, ma? So therefore, inside any metal, electric field cannot be present. Is it clear? Therefore, what is the note point here we have to write? A note point is that, okay, ma? Inside metals, electric field will be 0. Metals lopala electric field unde avakasame ledu. Why it is like that we have understood, no? Because there are many free electrons. and all those free electrons, they will develop an opposite field to the direction of applied field. Okay, but the same is not the case with the case of semiconductors or insulators. Okay, what happened? But in the case of semiconductors or insulators, okay, for example, if I take semiconductor or insulators, okay, here what happens, for example, this is the metal, okay, so just I am drawing the magnitude here, this is the external applied field, and induced electric field will be very small. Are you able to understand? Induced electric field will be very small when compared to applied electric field, because here free charges are very less, no? In the case of semiconductors or insulators, free charges or free electrons are very less. So induced electric field magnitude will be less than the magnitude of applied electric field. Is it clear? So therefore, in this condition, the net electric field will be how much? It is E external minus E induced. Okay? And E external is always greater than E induced. So this is what happens when you apply external electric field in the case of metals and non-metals or insulators or semiconductors. Clear? No? That's it. Okay. So next we are studying electric field due to charged metallic conductor. See, yesterday we have studied this one. No? For example, if this is a conductor, okay, and if you give charges to this one, charges will reside on both surface of the conductor. No? Charges will be present on the right side also, charges will be present on the left side also. So therefore, anywhere if you want to calculate electric field, if it is an infinite conductor, then electric field will be how much? It is sigma divided by epsilon naught. This is what we have studied, no? Electric field because of sheet of charges is sigma by 2 epsilon naught. But if you take a metal, charges are present on both sides, no? So therefore, net electric field will be how much? Sigma by epsilon 2 epsilon naught plus sigma by 2 epsilon naught, which is equal to sigma by epsilon naught. Okay? And similarly, if you take any irregularly shaped conductor also, okay, any irregularly shaped conductor also if you take, then because of this conductor also, outside, on the outside surface, how much will be the electric field? Electric field will be sigma divided by epsilon naught. Okay, just above the surface of any metal charged conductor, electric field will be same, E is equals to sigma divided by epsilon naught. Even it is a plate or even if it is any conductor of any shape, same magnitude of electric field. Okay, now can you say what is the magnitude of electric field inside this conductor? Inside surface it is 0. Already we have studied. No? For inside surfaces it is always 0. Okay. Now similarly, if I say that potential, electric potential on the surface of conductor, potential, electric potential on the surface of conductor, if it is V, okay, what is meant by potential? Potential ante gurtunda? Potential is nothing but work done per unit charge, no? Okay. See, if I start depositing charges on this conductor, okokka charge ni తీసుకెళ్ళి ఈ కండక్టర్ పైన డిపాజిట్ చేయడం స్టార్ట్ చేశాను అనుకోండి, then potential of the conductor continuously increases. Okay. So on the surface of the conductor, if potential V is equals to W by Q, then can you say what will be the potential inside of this conductor? Conductor లోపల పొటెన్షియల్ ఎంత ఉంటుంది? చార్జెస్తో నీకేం పని? What is meant by potential? Potential is work done per unit charge. That is called potential. No? It means if I want to bring any positive charge from infinity to the inside of this conductor, I did not do any work. Work చేయాల్సిన అవసరం లేదా? చేయాల్సిందే కదా మరి, జీరో ఎలా అవుతుంది? Are you able to understand? Electric field is 0. Electric field is 0, it doesn't mean that potential also should be 0. Are you able to understand? Potential may be 0, may not be 0. My question is, what is the potential existing inside of this conductor? Entuntu. Answer for this one is Sima. We have a relation between E and dV, no? E and V. What is the relation between E and V, ma? E is equals to minus dV divided by dr. This already we have studied, no? Relation between change of potential, change of distance and electric field. E is equals to minus dV by dr. So therefore, electric field inside the conductor is how much? 0. Clear, no? So 0 is equals to minus dV divided by dr. It means minus dV by dr is also 0. If dV by dr is 0, it means that potential should be constant, no? So potential is never 0. Potential is constant. Which potential? Potential existing inside the conductor is a constant. Constant means how much? Constant means the same potential which is existing on the surface. Same potential will be present inside the conductor also everywhere. Okay, ma? Therefore, what I write? Therefore, the same potential existing on the surface, will exist inside the volume of conductor also. Inside the volume of conductor also. Okay, ma? So therefore I say potential existing on the surface. Okay? This must be equal to potential inside the volume of the metal. Inside the volume of metal. Is it clear, ma? Surface paina enta potential untundo, metal surface lopala kudanu ante potential untundi. Is it clear? What is the reason we have studied, no, ma? Reason is E is equals to minus dV by dr. E is 0. dV by dr is also 0. It means potential is a constant. Okay? Make a note. Okay, ma? Similarly, if I give you one question, try to answer this question, ma? See, ma. So consider this is a charged metal conductor. Okay, ma? Consider this is a charged metal conductor. Okay? So this is point A and this is point B. So here there is a test charge Q0. I want to move this test charge from A to B. Then can you say what is the amount of work done? Anybody? Answer enta. Are you able to understand, ma? There is a charged metal conductor. Inside the volume of this conductor, I am taking 2 points, ma, point A and point B. So from point A, I want to move a test charge from point A to point B. Then what is the amount of work done? Apply చేయండి రా కొంచెమన్నా. ఎందుకు? Work done will be 0 definitely. Can you say why? Electric field లేకపోవడానికి వర్క్ జరగడానికి ఏం సంబంధం? Potential difference is not there, no? See, ma, throughout this volume of this conductor, just now we have studied, no? Potential everywhere inside the volume of the conductor is how much? Constant. Clear, no? It means what is the potential existing at point A, same is the potential existing at point B also. Point A దగ్గర ఎంత potential ఉంటుందో point B దగ్గర కూడా అంతే potential ఉంటుంది. And what is the equation for work done? It is nothing but VB minus VA multiplied by Q0. This is the equation of work done, no, ma? I am moving the charge from A to B. So potential difference, how should I take? VB minus VA multiplied by charge. Potential difference is not there, so I need not do any work. Okay? So therefore, inside the volume of the conductor is what? It is a equipotential surface. Our volume is what kind of volume? Equipotential volume. Equipotential volume means throughout the volume we have same potential. Okay? So make a note of that point also. సో వీటిపైన క్వశ్చన్స్ వస్తూ ఉంటాయి మా చిన్న క్వశ్చన్స్ వస్తాయి. ఇఫ్ యు ఆర్ నాట్ క్లియర్ అబౌట్ ద బేసిక్స్, ఇఫ్ సచ్ క్వశ్చన్ ఈస్ గివెన్, యూ విల్ లూజ్ 4 marks. Okay, so what are the note points we have to write? Note points are that surface or outer surface of any charged conductor. Okay ma, outer surface of any charged conductor is an equipotential surface. Is an equipotential surface. One more point is that the inside volume of any charged conductor is also an equipotential surface. Okay, so what are the 2 types of surfaces we are studying ma? First one is outer surface. Outer surface means this surface ma, this surface, this is the outer surface no? So this outer surface is what kind of surface? Equipotential surface. Are you able to understand? Equipotential surface means what, everywhere you will find the same potential. And even the inside volume of the conductor is also a equipotential surface. Okay, surface paina మీరు ఏ పాయింట్ తీసుకున్నా ఈక్విపొటెన్షియల్, వాల్యూమ్ లోపల ఏ పాయింట్ తీసుకున్నా ఈక్విపొటెన్షియల్. క్లియర్ నో? దట్స్ సిమా. సో వాట్ ఈస్ మెంట్ బై కెపాసిటెన్స్? కెపాసిటెన్స్ ఈజ్ ఎబిలిటీ ఆఫ్ ఎ బాడీ టు స్టోర్ చార్జ్. ఓకేమా? సిమా, సమ్ బాడీస్ దే కెన్ స్టోర్ small amount of charge, some bodies can store more amount of charge. That ability of the body to store a charge is nothing but capacitance. Clear? See, what happens is, if I take a metallic sphere, okay ma? If I take a metallic sphere and if I go on depositing charges on this one, okay, continuously I am depositing positive charges, then what happens? If I continuously deposit charges on this sphere, potential of the sphere increases, no? What is potential? E is equals to Q divided by 4 pi epsilon naught into R. This is the equation of potential due to point charge, no? Potential due to what? Potential due to point charge. But a sphere also behaves like a point charge. So don't be confused. Adi point charge ogada masare indi deeniki cheppinadu. This also behaves like a point charge only. Clear, no? Similarly, what is the equation to calculate electric field of this sphere on the surface ma? E is equals to Q divided by 4 pi epsilon naught into R square. If R is the radius of this metallic sphere. Charges are present continuously on the outside surface, no? Are you able to understand, no? Continuously I am increasing the charges, so potential increases, electric field also increases. So make a note of that point. What is the note point I have to write? If we start depositing charges, clear nama? Then potential and electric field of the conductor increases continuously. Okay? Continuously the electric field and potential of this conductor will continuously increase. Now my question is, I can deposit like this charges for how much time? ఇలా ఎంతసేపు నేను ఛార్జెస్ని డిపాజిట్ చేస్తూనే ఉండొచ్చు? ఫుల్ ఎట్లా అవుతుంది రే ఇది? Charges are there, don't have any volume and size and shape, nama. Electrons are very, very small particles. Clear? Definitely you cannot fill their volume. See, if I continuously start adding charges onto this one, at one point of time this electric field strength will be equal to the electric breakdown strength of air. Air is an insulator, no? Air is what? Air is an insulator. Current pass అవుతుందా ఎయిర్లో? పాస్ అవ్వదు. అయిందంటే పోతాం, ఇవన్నీ పనిచేయ మనకు వచ్చి తగులుతూ ఉంటుంది కరెంట్. ఎయిర్ ఈజ్ అన్ ఇన్సులేటర్ మా. And what is the insulation capacity of air? Air has a breakdown strength of E is equals to 3 into 10 power 6 volts per meter. Okay, ma? So if I continuously start depositing charges on this metallic sphere, then what happens is, at one point in time, the field on this conductor will become this much. Okay, ma? Conductor paina yanta field develop avutundi, field equal to 3 into 10 power 6 volts per meter field will be developed. And this field is exactly equal to breakdown strength of air. Breakdown strength of air means what? If air sees this much amount of electric field, air will forget its non-conducting nature and it starts conducting electricity. Are you able to understand, ma? So after reaching this electric field, what happens is, I deposit one charge, one positive charge, and one positive charge will be leaked into the atmosphere. Clear, no? I deposit one more electric charge, and that charge will be leaked into the atmosphere. Are you able to understand what is happening? So it means that I cannot charge a body beyond a certain limit. Oka value kanna manamu body ni charge cheyalem. Is it clear? So make a note. So if at some point the field of body becomes equal to breakdown strength of air. Breakdown strength of air. Okay, ma? And so air starts conduction. Air starts conduction. So body cannot be charged further. Body cannot be charged further. Is it clear, ma, what is happening? Field, electric field strength perugutu, it reaches the field strength of 3 into 10 power 6. Now after this, if you increase the electric field, now air behaves like a conductor, and whatever charges you add onto the metal surface, they will be leaking into the atmosphere. Okay? So therefore, what is the point which I am making to prove here? Point is that, therefore, any body cannot be charged infinitely. Okay, ma? Infinite charging of a body is not possible. We can charge a body only up to certain limit only. Okay? So always there is a limit of charging bodies. Clear? If there is no limit of charging bodies, we are very intelligent people. Ma. What we will do is, 1 second. Yedo answer cheppinattu cheptivedra. Clear, ma? See, ma, if there is no limit of charging, what we can do is, in rainy seasons we will get thunderstorms, no, ma? If I can store that thunderstorm, I can supply energy for the whole for 20 years. ప్రపంచానికంతా 20 సంవత్సరాలకు కావాల్సిన ఎనర్జీని మనం సప్లై చేయొచ్చు. If I can store one thunderstorm. Clear, no? But we don't have that much ability to store charges. What is the reason? Already we have studied. No? If I start depositing charges, at some point of time they will continuously leak into the atmosphere. So infinite charging is not possible. Clear? See, ma, charge stored on a body, is directly proportional to potential difference on the body, or just you can say potential of the body also you can say. So therefore it means that Q is directly proportional to V. Okay, ma? What is meant by Q? Q means what? Charge stored on a body. V means potential present on the body or potential difference on the body. Are you able to understand, ma? If there is more potential difference, it means more charge is present, no? Because what is the equation of potential? V is equals to Q by 4 pi epsilon naught into R only, no, for spherical bodies. So Q is directly proportional to V. More potential difference, you are able to store more charge. And the amount of storing of charges depends upon capacitance of the body. So therefore, if I want to remove this proportionality symbol, I have to place a constant. and that constant is nothing but C. Okay, ma? So what is meant by C here? C is called as capacitance of a body. Okay, and how can I define capacitance? Capacitance is nothing but a charge stored per unit potential of the body. Q by V means what, ma? For 1 volt of potential difference, body is able to store how much charge? That capacity is called as capacitance. Is it clear? I supply only 1 volt of potential difference. Then I check bodies are able to store how much charge. Some bodies, they can store more charge depending on the size, the shape of the body. Some bodies can store very little charge. Are you able to understand? So how much charge they are storing for a particular amount of potential is called as capacitance. Okay, so therefore write the definition of this one. Capacitance, how can I define? The amount of charge stored per unit potential or potential difference. That is called as capacitance. Okay, that is called as what? That is called as capacitance. Understood now? See, ma, let us try to understand this one by taking one example. See, for example, this is one small metal sphere and this is one very big metal sphere. Okay, ma? So I will give Q amount of charge on both of them. This one is having a radius of R1 and this one is having a radius of R2. And definitely I can see that R2 is greater than R1. But on both the metallic surfaces I am giving same amount of charge. Plus Q charge, here also plus Q charge. Now can you say on which body more potential will develop? R1. On R1 more potential will develop. How can you say? Radius is? That's it. Okay, ma? V is equals to Q divided by 4 pi epsilon naught into R, no, ma? This is the equation for potential for point charges as well as metallic spheres. Clear, no? So volume is inversely proportional to radius, no? Sorry, potential. Potential is inversely proportional to radius. It means that if radius is very large, then for the same amount of charge, potential developed will be very less. That's all, no, ma? Here what is a constant here? If V and R, if they are inversely proportional, it means Q should be constant, no? Q should be constant, no, ma? Then only I can take proportionality results. Okay? Therefore, on both of them, here if V1 potential develops and here if V2 potential develops, definitely I can say V1 is greater than V2. Definitely V1 is greater than V2. Why V1 is greater? Because radius is smaller. No? Clear, no? Radius is smaller, so potential developed will be greater. Deenipayina ekku potential develop ayipotundi. And on this one, very small amount of potential will develop. Okay? If potential is greater, definitely field also will be greater, no? If potential increases, field also increases. If a field increases, it means I can store very less amount of charge on this one, and on this one I can store more amount of charge. Are you able to understand? If I add a very small amount of charge, its potential increases by large value. If potential increases by large value, field also increases by large value. So on this small conductor, I cannot store huge charge. But on this one I can store very huge amount of charge. Because radius is bigger, size is bigger, potential is less, field also will be lesser. That is the reason. Have you understood, ma? That's it. So therefore what I say here, therefore, on bigger sphere, okay, ma, more charge can be stored. More charge can be stored before electric breakdown of air. Before electric breakdown of air. Okay? That is the concept. Sima. Now we are studying how actually we charge plates of a capacitor. Sima, generally capacitor will have two plates now, one positive plate and second one is a negative plate. So initially these plates are uncharged. Initially when I connect them to a battery, they don't have any charge. But immediately when I connect this one to a potential difference, here we have positive charge number. This positive charge, it starts attracting electrons from this first plate. Are you able to understand? Positively charged terminal, it starts attracting electrons from the positive plate of this capacitor. So these electrons, they travel continuously and they get deposited on the second plate. Okay, ma? So this plate will continuously gain negative charges, and this one is losing negative charges, no, ma? So this will become positively charged plate. Are you able to understand what is happening? Electrons are continuously transferred from one plate to another plate. So one plate become positively charged and the second plate will become negatively charged. So here the point is that charges always reside on the inside surface of the plates only. Charges doesn't reside on the outside surface. They reside only on the inside surface. What is the reason? What is the reason? Reason is these are positive, these are negative. Continuously they are attracted towards each other, no? Clear, no? So all the charges they get deposited on inside surface. Similarly, negative charges also they get deposited on the inside surface. Okay. So if this is what is happening, now can you say what is the direction of potential which has developed? Okay, ma? So direction of potential is, this is the direction of electric field which has developed, no, ma? Okay. This is the direction of electric field which has developed. So until the potential between the plates reaches to the potential of the battery, so this transfer of charges will be happening continuously. So these charges will flow to the second plate up to which time? Until it gets the same potential difference as that of the battery. Battery has a potential difference of V, no? So same potential difference should develop between the plates of the capacitor also. Until then, these transfer of charges will continue. After that, the transfer of charges will stop. That phenomenon is called as charging of a capacitor. Are you able to understand how electrons are transferred? Clear, no? So write down. So if uncharged plates are connected by a battery, okay, ma? Then electrons get transferred. Electrons get transferred from one plate to another. From one plate to another. So potential between the charges, potential between the plates, ma, potential between the plates increase. Okay. And when potential between the plates is equals to potential of battery, then charges will stop. Charges will stop transferring. Okay. So until potential difference becomes equal, these charges will travel. After that, the traveling of charges will stop. So this phenomenon is called as charging of a capacitor. Okay. That's it. Now if you remove this battery also, nothing will happen. If you remove this battery, charges will be present as usual on the plates of the capacitor. Okay. And one more point is, what is the charge present on the positive plate? Same amount of negative charge will be present on the next plate also. Ante kada? If from here one electron goes and reaches here, here one positive charge will develop. Equal amount of negative charge also develops on the second plate. Sima. So completed, no? Sima, unit of capacitance. Unit of capacitance. Yesterday we have studied about capacitance, no? So charge stored on a capacitor is directly proportional to potential difference, no? So therefore Q is equals to C into V. So therefore C is equals to Q by V. Okay. So therefore what is the unit of charge? Coulombs. What is the unit of potential difference? V. So C by V is the unit of capacitance. And this C by V is also called as, or 1 coulomb per 1 volt is also called as 1 farads. Okay, ma? 1 coulomb of charge stored per 1 volt of potential difference, that unit is called as 1 farad. So that is the unit of capacitance. Clear? Right. Okay, ma? So see this. So now we are trying to derive a relation for capacitance of a spherical conducting sphere, ma. So this is not a parallel plate capacitor. Capacitor means we should have parallel plates, no? This is not a parallel plate capacitor. This is just a metallic sphere. Okay. Yesterday we discussed, as we go on adding charges on this one, until it reaches the potential difference of our dielectric strength of air, we can go on adding charges on this one. After that we cannot add. So for this metallic sphere, I want to calculate the equation of a capacitance. Okay, ma? So what is the basic equation of capacitance? C is equals to Q by V. This is the equation, no, ma? What is Q? Q is the amount of charge present on this sphere. V is the potential difference of the sphere. Okay. Sphere behaves like a point charge. No? So therefore, what is the equation for calculating potential of a sphere? Q divided by 4 pi epsilon naught into R. That's all. No? So just substitute in this equation. So therefore, C is equals to Q divided by, instead of potential I can write Q divided by 4 pi epsilon naught into R. So Q and Q gets cancelled. So C is equals to 4 pi epsilon naught into R. Okay, ma? So this is the equation to calculate capacitance of a spherical capacitor. This is not a capacitor, ma, you cannot say. Spherical conductor. Spherical metal conductor. Understood, no? So if this capacitor, or capacitor we should not say, no? If this conductor is placed, this is a case, ma, is placed in a medium of dielectric constant epsilon, okay, ma? Then dielectric constant ER, where ER is equals to E divided by E naught, okay, ma? Then in this condition, okay, then capacitance C is equals to 4 pi epsilon R. Or you can write C is equals to 4 pi epsilon naught epsilon R multiplied by R. This is the equation. Okay, ma? So this is one case, ma. Case means what? Previously this metallic sphere medium was air, no? Medium was air. So instead of placing this one in air, if I place in another medium whose dielectric constant is ER. Dielectric constant means relative permittivity. Another name for relative permittivity is ER. Okay. Then here instead of epsilon naught, I have to write epsilon only, no? Where epsilon is the dielectric strength of that particular medium. This is for air. Epsilon naught is what? Epsilon naught is for air. And this is epsilon is for any medium. Okay. But we have this relation, no? What is the relation between epsilon, epsilon naught and relative permittivity? Relative permittivity is permittivity of medium divided by permittivity of free space. So therefore epsilon, I can write epsilon naught into epsilon R. So therefore this is one more equation to calculate capacitance if this spherical conductor is placed in another medium. Okay, ma air kaakunda vere medium lo place chesina. Okay. See this question. Assuming Earth to be an isolated conducting sphere of radius 6,400 kilometers, what is the capacitance of Earth? Sima, Earth is also a sphere, no? It is not a perfect sphere, but definitely it is a sphere only. Okay. So on this sphere also we can store charges, no? Earth can store the charges very well. Bhumi charges ni brahmananga store cheskuntu. Okay. So this is also a natural method of storing the charges. So if you consider radius of Earth to be 6,400, then what is its capacitance? How can I solve? It is in the form of a conducting sphere only, no? What is the capacitance of a sphere? Capacitance of a sphere is equals to 4 pi epsilon naught into R. This is the equation, no? 4 pi epsilon naught value is how much? 1 into 1 by 9 into 10 power 9. multiplying what is the radius of Earth, 6400 multiplied by 10 power 3. Okay, so if you do this total calculation, you will get 711 into 10 power minus 6 farads, which can also be written as 711 microfarads. So that is the capacitance of Earth. Clear, Nama? See here, capacitance of Earth is, see how much? 711 microfarads, 10 power minus 6. Earth is a very big sphere, no? But still capacitance is very small. It means that farad is not a small unit, ma. Farad is a very, very big unit of measuring capacitance. Okay, even for Earth also it is only 711 microfarads. See this question, ma. Question is 27 spherical drops, each of radius 3 millimeter and carrying 10 power minus 12 coulombs of charge are combined to form a single drop. Okay, ma? Initially there are many drops, many small drops. 27 drops were there, and they were combining to form a bigger drop. That is the concept. Then you are supposed to calculate a capacitance and potential of the bigger drop. Clear, ma? See, ma, if I combine all these drops, what happens? It drops nanta combine chesthe emutundi. It forms a bigger drop. Still? Ante. See, ma, what is the total charge present on all these drops? That total charge will be present on bigger drop also, no? Okay. So therefore, what is the total amount of charge? Total charge on bigger drop. Okay, ma? Total charge on bigger drop will be how much? It will be equal to 27 multiplied by 10 power minus 12 coulombs. This is the charge on bigger drop. Clear, no? Similarly, to find out capacitance and to find out potential, first of all, I need to require what is the radius of this bigger drop, no? Because without radius, we can't do anything. Because the equation of capacitance for a sphere is 4 pi epsilon naught into r, no? Radius I require. Radius, how can I calculate? Radius of bigger sphere. How can I calculate, ma? Radius of bigger sphere. Okay, see, ma, volume of 27 small drops is equal to volume of bigger drop, no? BD cigarette lo gadadi. BD bigger drop adi. So volume of 27 small drops is equals to volume of bigger drop. Okay, so therefore 27 multiplied by 4 by 3 pi r cube is equals to 4 by 3 pi capital R cube. That's all, no? So 4 by 3 pi get cancelled. So if you take cube root on every side, 3 small r, this is small r. So 3 into small r is equal to capital R. That's all, no? So therefore capital R radius is so much? 3 times of, what is the radius of small drop? 3 mm. So 3 into 10 power minus 3 meters. Clear, number? So radius of bigger drop is how much? It is 9 into 10 power minus 3 meter. That is the radius of the bigger drop. Up to here it is clear, no? So once I calculate radius, very easily I can calculate the capacitance of bigger drop. No? What is the equation of capacitance of a sphere? It is 4 pi epsilon naught into r. That's all, no? 4 pi epsilon naught value is how much? 1 by 9 into 10 power. 1 by 9 into 10 power 9 multiplied by radius is how much? 9 into 10 power minus 3. I mean, I can the one say sound winter tuck down the gundala saratla. So if you do this calculation, you will get capacitance. Okay, ma? So capacitance which you should get is 1 picofarad or 1 into 10 power minus 12 farads. This is also called 1 picofarad. Okay, ma? Is it clear? So this is the capacitance which you will get. Are you able to understand? So once I calculate capacitance, I can calculate potential also. No? Huh? How can I calculate potential? Potential, how can I calculate? So C is equals to Q by V. So therefore V is equals to Q by C. That's all. No? So therefore potential on the capacitor on this conductor is how much? Charge. What is the total amount of charge? 27 into 10 power minus 12. Divided by capacitance already we have calculated 1 into 10 power minus 12. So V is equals to 27 volts. That is our answer. This is 10 power minus 12 is the charge possessed by a single sphere, no? Single small sphere. When you combine them, charge becomes 27 times, no? Charge of bigger sphere is how much?
27.
Charge of smaller sphere is how much? Smaller sphere only 10 power minus 2. 27 drops are there. So 27 into 10 power minus 12. Divided by capacitance of bigger one is 1 picofarad. That's all, 27 volts. Okay? Sima. So next we are studying about capacitance of a spherical capacitor. Spherical capacitor, Sima, any capacitor will have two parallel plates. Will have two parallel plates. Clear, no? Always we place two plates in parallel for a parallel plate capacitor. So this is also a parallel plate capacitor only, no? Huh? So inner sphere and outer sphere, they are parallel to each other, no? So therefore this also behaves like a parallel plate capacitor only. Are you able to understand? Okay, Vinali. Is it clear, ma? Every capacitor is a parallel plate capacitor. So what is the reason that we place only parallel plates? That reason first of all we should know, ma. See here. Consider this is a positive plate and charges are present on this positive plate. Okay, ma? Charges are present on this positive plate. So therefore, because of this plate, Vinandi careful, because of this plate, somewhere at this point, or even on the same metal only you take, on the same plate here at point A, potential will be how much? Potential will be, let it be 10 volts. Are you able to understand, ma? Because of this charged plate, on the surface of the same plate, potential is how much? 10 volts, for example. See, my potential is 10 volts, then if I go on adding charges to this one, then after some time I cannot store more charges, no? Because it reaches to the breakdown strength of air, and after that if you add charges, they will be leaking into the atmosphere. Okay? So therefore what I do is, I will take another plate. Okay, ma? I will take another plate with negative charges. Are you able to understand what is happening? I will take another plate with negative charges. And here on this point B, potential on this point B is minus 10 volts. Because what are the number of charges on positive plate, same number of charges should be present on negative plate also. So positive plate will give positive potential, negative plate will give negative potential on their own surfaces. But if you take a point A is at a larger distance from this second plate, no ma? So therefore, second plate will give, let us consider potential given by second plate on first plate, it is minus 6 volts. See, ma, if distance increases, potential decreases, no? If distance from the charge increases, what happens to potential? Potential decreases. So now I am discussing potential because of negative plate. On its own surface, it has how much potential? Minus 10. But I am discussing potential given by second plate on first plate. First plate is at a greater distance, no? First plate is at a certain distance of D. So therefore, its negative potential on the first plate also will reduce. ఈ ప్లేటు దీనిపైన ఒక నెగటివ్ పొటెన్షియల్ ఇస్తుంది కదా, ఐఎమ్ డిస్కసింగ్ అబౌట్ దట్. క్లియర్? అండ్ ఇట్ విల్ బి హౌ మచ్? ఇట్ విల్ డెఫినెట్లీ ఇట్ విల్ నాట్ బి minus 10, no? It will be less than minus 10, minus 6. Is it clear? So therefore, what is the net potential on A now? Net potential on A is how much? Initial potential was 10. And potential given by negative plate is how much? Minus 6. So total potential? 4. So potential has decreased to 4. If potential decreased to 4, it means you can add more charges. Are you able to understand? If potential increases, field also increases, no? But for same number of charges, I am making potential to reduce by introducing one more plate. Is it clear, ma? Potential reduces. If potential reduces, I can reduce the field also. If field reduces, I can add more charges. Okay? So therefore, to increase the storing capacity or to increase the capacitance of a capacitor, we plate a negative plate. Always we place a negative plate so that capacitance of the capacitor increases. And how capacitance increases? By reducing the potential. Because what is the equation of capacitance? C is equals to Q by V, no? So let us consider Q is a constant. Same amount of charge is present, no? But if potential is reduced, capacitance automatically increases. That is the logic of placing a parallel plate capacitor. Are you able to understand, ma? So write down. So make this total data, then we will write some statements about that. So what you write? Reason of placing parallel plate. Reason of placing parallel plate. So this is not in our syllabus, ma, just for your understanding purpose, so that you can understand the nature of capacitance. Okay? So therefore what we write? So therefore we write down a small statement about this. Introduction of oppositely charged plate. Introduction of oppositely charged plate reduces potential on first plate so that more number of charges can be added. More number of charges can be added and capacitance increases. Clear, Nama? That is the reason of placing a parallel plate capacitor, which is opposite in symbol. Fine? Sima. So this is also a parallel plate capacitor, no? Because there is one inner sphere and there is one outer sphere also. So these two plates always they are parallel to each other. Okay, ma? Now what I do is I give some charge to the inner sphere, ma. I give some charge to the inner sphere. So this charge will induce equal amount of negative charge on the inner plate of the second sphere. Arthamatunda em jarugutundo? I am giving charge to which sphere? Inner sphere. Okay, ma? Already we studied that this is the method of charging by induction process. No? What is meant by induction process? If I place a charged body, uncharged body close to each other, charged body will attract opposite charges on one side, and like charges will flow to the other side of the sphere. That method of charging is called as induction. Same concept here also. I give charges on the inside of the plate. So these charges will attract negative charges on the inner surface of the second plate. So if negative charges are deposited on the inside surface, it means the positive charges will deposit on the outside surface, because outer sphere was neutral, no? We are giving charge to which sphere? Inner sphere. So it is not neutral. Inner sphere is not neutral. But to this outer sphere we are not giving any charge. So it was a neutral body. So neutral body means what? If on one side negative charges are deposited, on the other side positive charges must be deposited. Are you able to understand? So therefore what I do is, I will connect this outer sphere to earth. Dinni nenu earthing chestanu. Okay, ma? Earthing means what? We connect this outer surface of the outer sphere to ground. And ground is a very big body, no? Earth is a very big sphere, no, ma? Whatever charges are present on the surface, it will attract. It means all the positive charges, they will flow to the ground. And here, now there are no charges. Charges will get disappeared. Are you able to understand? So this is the construction of a spherical capacitor. Okay? And the amount of charges stored are, these are the charges. Okay? These are the charges which we have given, and these are the charges which are induced. And the charges which are induced on the outer surface, they are flowing to the ground. Fine? Okay, ma? And what is the equation of capacitance of this spherical capacitor? 4 pi epsilon naught RA RB divided by RB minus RE, where RA is the radius of the inner sphere, RB is the radius of the outer sphere. Okay, ma? And this is in which condition? If the gap between these plates is air. Gap between the plates is air or vacuum. Instead of that, if I place any other material, for example, if I place water, if I place any other material, then the equation of capacitance is this much. 4 pi epsilon RA RB divided by RB minus RE. And what is epsilon? Permittivity of that particular medium. Are you able to understand? No? Or we know that ER can be written as E divided by E naught. No? So therefore, epsilon, how can I write? I can write ER into E naught. So therefore, same equation how I can write. So capacitance, when a medium is placed, it is a 4 pi epsilon naught epsilon R RA RB divided by RB minus RE. This is the equation. Understood? No? So just instead of epsilon naught, I am writing epsilon. But epsilon can be written as epsilon naught into epsilon R. So I can write like this. Fine? Right.